So I wanted to bring us back to the notion of structure-function relationships. I have a fairly slightly more elaborate slide that now is going to try to summarize many of the types of architectures we've been discussing so far, many of which you've already acquired, some still to fill up. And so that's how we're going to begin today. The recurrent neural networks in brains, you've already got a flavor for when we were looking into, for example, DTIs, right? So we were looking into the connections between different areas, and you saw in those blocky adjacency matrices that there were a lot of recurrences in the networks, and it would seem as if areas do like to send and receive from the same areas where they got from. That's actually the essence of recurrence. Anyone is able to produce a definition of recurrence as in opposition to feed-forward neural networks by now?
Yep, briefly. That so the signal in the feed-forward network would just propagate forward, and recurrent it would come back to every node it gets from, just simply. That's
all there is to it, right? So, and in the visual cortex, there is a lot of recurrences. The recurrences are also thought for amongst other things, to solve the problems of backpropagation. So we think the backpropagation is not completely plausible in the context of biological brains, although it's the main training mechanism we use in feed-forward artificial neural networks. And the schemes that have been suggested to basically substitute backpropagation have a lot to do with the recurrences and Hebbian learning. So the idea is really not unlike those that I have been trying to put forward also in the project, in which you have certain statistical regularities in input that are then acquired in a random network at first, and eventually organized. Now there's more than just activity-dependent plasticity for self-organization. There's certainly a pretty good role for hardwiring too. And I wanted to discuss a little bit about evolutionary robotics in a moment to create some metaphors for what do we think could look like hardwiring. And you know, recurrences are just about everywhere. The size of these arrows that go back and forth, they might not reflect the actual weights between these connections, but it's so common that to see a set of visual networks, or in fact, any networks that have these, you go there and then you come back. So it is a very common motif across the brain, recurrences, but at least between areas. This area sets that, and then it sends it back. There are, amongst the many functions that one talks about in this recurrence, one of them is prediction, for example. So if one area has done some processing and it sends it back to the other area, so in a sense that back projection can already carry some information about what the eye expects to see, for example. So if you're thinking about the visual cortex and LGN and the back projections that exist between them, when the visual cortex has now done the processing by grouping together, for example, a set of receptive fields and then transmitting it, the LGN receives connections from the units that have been activated saying, okay, maybe I've seen a line oriented in this direction or that direction. So those can work as priors. You know, if you've heard much about priors before, but those are in Bayesian probabilities, priors are knowledge that you have about a problem. So, you know, some extra information that you acquire through experience you acquire, and then you can project back on the world and make predictions, right? So a good prior allows you to make a good prediction. So if you have the window closed, your prediction about whether it's going to be sunny or or rainy, maybe at chance levels. But if you open the window, then you know immediately you have information. Now these are priors, and these priors are probably propagated also in the context of the brain. So this is another way in which recurrence has a functional role to play in the organization of brains and in the functional activity of brains. But let's first look at it from a slightly more distant perspective, because I've been talking about pattern recognition and hierarchies, and we've been talking about pattern recognition and hierarchies and functional localization in the context of invariances too, such as the neocognitron. Now those don't have recurrences, but in a sense, what Fukushima done with the neocognitron by training it via Hebbian learning is actually, I used the word a couple of times relating to his work, prescient, because it is what now people like Peter Roefsoma in the NIN, the Netherlands Institute for Wetenschappen, he is suggesting these types of schemes in which Hebbian learning back projections are creating the equivalent of back propagation. So even though pattern recognition in deep neural networks looks like it's feed-forward only, because we have a back propagation necessary to pass it back, or because we use Hebbian learning to transmit back that information, in a sense, algorithmically, we have already put some recurrence in the process. It's funny, you know? I mean, even though we talk about feed-forward neural networks only, in order to train them, you have to pass the information back. You have to get the error to be back propagated. However, feature extraction and convolutions in the visual stream, they would seem as if they are most, you know, feed-forward. You have a filter, and then you get a feature extraction out. But even there, it is thought that the convolutional filters in the brain are taught, and they're taught also via recurrences and backpropagation. So even though we can imagine what a receptive field would look like for a vertical line, and we can create a theory, the burden of explanation has to tell us why this organization is there. And usually when we get to that point, we're already involving some sort of recurrences. Today, you will see how recurrent neural networks can perform things like pattern completion. And particularly, I will bring you to the site of a fella, Jack Terwilliger. And he's basically programmed a set of, amongst other things, a Hopfield network also to see how an initially randomized input can settle onto a stored saved memory. So this is the essence of Hopfield networks. And here I'm just basically demonstrating what we're going to go through, and you're going to go through this in two different ways here, like in this little demo, and also here in the recurrent neural network Hopfield Necker cube project we put together. Hopefully this one is a little bit more or a bit smoother than the other project we had before. In any case, so this is the I know I'm not sure. I'm doing something, and I'm doing something on my other screen, and I didn't. As I'm talking, I'm actually doing this. I'm creating some noise in an input pattern, and I am using a Hopfield network here to bring it back to a memory pattern. So that's actually what I was trying to show to you a moment ago. I don't know if you see the steps, or whether you just see a pattern. Like so here, I randomize the pattern a little bit, then I clean it up via Hopfield network. So that's the idea of pattern completion. Sorry, I had my screen sharing in the other one.
So that this network cleansed up on its own.
Yeah, exactly.
Okay.
Yeah. So it does a number. So one of the things that we think that the Hopfield network is doing is pattern completion. We also do interpolation via it's like denoising, as you just saw. So that what we saw was more like denoising, and it can do, as we talked about before, it can do mergers between ideas. But this is something that we something that we still to discuss. So decision making, let me actually just tell you quickly how decision making is related to mutual inhibition. If you have multiple things you want to do at the same time, there's usually only a finite bandwidth you have to actually do things. You have to decide. And so in order to not to want to do the thing that you thought you might have wanted to do at the same time as you were thinking about doing 5 other things, you have to suppress them. And that's effectively, there's no mystery to what we think and most modern models of decision making really look like. Now, the degree to which you suppress, in the context of suppression, those things matter, and you can encode them in networks as well. But the essence of the problem remains that this, not that, that says no this. And this happens at the level of the basal ganglia. I'm not going to impact the same way as we're not, I don't know if you've noticed, in the computing brain, we're not really looking into specific models of specific organs, big model of the hippocampus, big model of the basal ganglion, big model of the thalamus, big model of the cerebellum, big model of the cortex. We're staying at the level in which these metaphors, these functional metaphors are available, because these are effectively what people try to embed in the complex models. Right, so I just say here, the example is the basal ganglia, and it's the interaction between the globus pallidus interior and the globus pallidus exterior as they interact with the thalamus and cortex. But those become circuit specificities that are absolutely gorgeous and beautiful to look at, but involuted with respect to the knowledge. And I want to first to give you the sense that, you know, decision making, mutual inhibition, because when you look at the brain, this is what you get. And often we're missing the woods from the trees in the sense that if we're talking about receptive fields and we're giving them a label like FEF, you immediately forgot how they look like, how their topology looked like, how they potentially self-organize. Our labels are incredibly helpful for us in terms of anatomy, but not necessarily as helpful to us in terms of really understanding the brain. And we need to combine this with a functional understanding of what are the functions to be performed. So apologies for belaboring this point, but I see way too much neuroscience that is just about doing another, you know, microscope, faster, better, more. And I think that in order to understand, you have to put your mouth where your money is. You have to basically try to say, okay, so how does then we suppress this set of networks so that the other networks can exist? Or how does a place cell emerge from nothing? It cannot be encoded genetically. So, you know, sorry, don't mean to belabor. Now, you had some of the simple ones that we talked earlier about, you know, contrast enhancement has to do with lateral inhibition in the retina and in the LGN. It might have already seen the convolution little Jupyter notebook that is in Canvas that was put together by Sam. It's very cool to go through because it has a little bit of an illusion that comes from the idea of lateral inhibition. So this is not mutual inhibition, but simply lateral inhibition. We talked about Hasha detectors before and how delays in filtering can do motion detection. And now let me give you another idea. I just mentioned that it could be that feedback projections from the visual cortex to the LGN are doing a little bit of prediction. Now, the high-shot model is effectively comparing now with the past to know where things are moving. So this is a motif, a functional motif that actually propagates in other areas of the brain as well. So with the Breitenberg vehicle, we saw that the just basically putting two sensors and two motors and crossing them with very simple anatomy via embodied robotics and via feed forward and feedback loops, we can create interesting behavior, even though it lacks the complexity of a brain. It can basically behave. It's nice to think that, you know, not all life has a brain, and a lot of the life does very important in things like in very simple ways. There's one thing that I'm still going to talk about. It's going to be next week, called autoencoders. And this is the idea that networks compress, but it relies on what you're going to learn today about Hopfield networks before we can get there. So this is still to come. And then there are two beautiful topics that I wanted to cover today to a certain extent. One is sequence generation, right? When you're talking, we're producing sequences of phonation apparatus contractions, like air has to come at the right side. Like the contraction of the vocal cords has to be, you know, producing a little bit of a time series there. These are very well symbolized by the idea of reservoir networks, and most definitely they require recurrence because of history. You need to know where you were, what you just done, to know where you're going to go next. In a sentence, everything is connected end to back, right? So we're always interpreting it backwards. And, you know, to me, Hopfield networks and the reservoir networks, this is something we found out. This is something really that recurrences and attractors, they will be the future of the language that we will use to understand the more complex brain functions and cognitive functions such as memory. Even if our models, like right now, sometimes they seem simple, sometimes they seem really complex too, in terms of, you know, deep learning recurrent neural networks with LSTMs, long short-term memories. Their architectures can be rather complex. But the problem that they are solving is truly the problem of knowing what comes next once this has come. So, and this, I think, is well symbolized by whatever it is we're going to be seeing today. Recurrent neural networks, 9:30. So the functions that recurrent neural networks perform could, to my mind, be summarized in this small little set here. So for one thing, spontaneous dynamics is about a recurrence, right? Sometimes, for example, if you want a neuron to be self-sustaining and the neuron to be resonating, it has to have an interplay between spike and the hyperpolarization. So in a sense, it's the same kind of idea. One goes up, like with a positive feedback, and then the other one goes down, but pushes it sufficiently down so that you activate the spring. One calls the other. It's not different. If neuron one in this side like activates this other side, then that the other neuron will be active, and so on in a cascade. It's important to realize, however, that these cascades, so especially in the cerebral cortex, where you have synapses being insufficient to drive neurons. So a single synapse is insufficient to drive the other neuron spike. You really need a lot of synapses. So you need that kind of criticality from the project 3. From this spiking neural networks. You need to understand that in order to get that system running, one neuron spiking is not going to be sufficient. You're going to have a lot of neurons spiking and distributing those spikes to each other so that they can basically cross criticality to create spontaneous dynamics. So spontaneous dynamics is not simply a matter of having a recurrence. You also have to have some sort of generation mechanism, like for Poisson or for noise, something that often the basal ganglia has been tasked with. people have said the basal ganglia is a thought pump. And that's because it has a lot of spontaneously firing neurons that are spontaneously distributing information up and down. Now, clearly, spontaneous, quote unquote, but you have a motor. You have someone that is pushing them. And because you generate these spontaneous dynamics, you also generate sensory motor patterns that you also know, not by immediate consequence, but by the fact that spontaneous dynamics may sometimes push, let's talk about spontaneous dynamics on the arm. Right, so let's talk about what drives our muscle system to have a posture. You have to organize those spontaneous dynamics into the actual contraction patterns that will create a posture. Now, this is also not unlike a sequence such as the one that is coming out of the mouth. When Broca's area is the area that is where my grandfather got a stroke in his Broca's area. He was able to speak 7 languages, and then suddenly he was able to speak half a language, or less, much less, actually, a few sentences. And it's very interesting to think about what Broca's area is actually doing. Because it was the phonation, really, the connection between how the word, he could still read, obviously. So Broca's stroke usually does not impair your word comprehension, only the word production. You don't know how to move your mouth anymore. And you could see him. It's not coming out right. I mean, so these sequences are not being properly encoded. This is nothing but the same type of generating patterns that we do in like more complex sensory motor or bodily sensory motor. So not unlike means I have to listen to myself to be able to produce well-sounding speech. Now, I remember that we talked when Chris was talking about playing the piano without listening is possible, but you probably have some slips, to say the least. And so you will need a little bit of the feedback and in order to produce the sequence, obviously we'll have to have trained it for a long, long time. Now, is this so different than what it is to, have a sequence of concepts in the mind, sort of like retrieving mental imagery? So ultimately, what we have is a type of a dynamical reservoir. Everything is generative. We're producing stuff. So memory is not encoded in some sort of like a bit flip in a RAM, in which you just basically flip the bits in the right way and you hold them that way, and then you have the memory. So that's what happens to the computer. In the brain, no, it's like you're going to have to use those tubes. You're going to have to pump that information back through the brain again. And then the brain, by virtue of having had the experience, has their connections arranged in a certain way so as to produce the functional pattern. With this, what I wanted to really give you the impression of is, again, remember back in the day, I started saying everything is a sensory motor pattern. Everything is a spatial temporal pattern in the sensory system. And now I'm saying that everything in cognition is some sort of a dynamical reservoir, some sort of a pattern being generated, some sort of a sequence being encoded and reproduced. So, all of this is about the same thing. So connecting the ideas, at least at this very abstract level. And without further ado, I come to the idea of recurrent neural networks and attractors, if you allow me. So I often debate with myself whether I should first present Hopfield networks because they're a simple way to look into this, or first I should look into reservoir networks. But because you've done simple networks project before, So the simple networks project is the one in which you basically just simply have a recurrent neural network that by initializing it, sometimes you converge onto an initial state. But you already know kind of like in the back of your mind how a recurrent neural network is structured, especially like in this very abstract space of, so the recurrent neural network is organized in this computational way, in this really our simplified metaphors of this. And that brings me to some of them. So particularly, I wanted to talk to you about, and where are they? Because, oh, here. So a liquid state machine, for example. Liquid state machine is a type of reservoir network. The other one is an echo state machine. Where is it? Here, echo state network. So the echo state network and the liquid state machine, they look very similar from their, as many of these networks do in terms of their wiring. Long story short, both of them are recurrent connections, just as the ones that we had in the simple network problem, with certain features in terms of the weight matrix. The weight matrix shouldn't be too large and it shouldn't be too small. It shouldn't be completely chaotic and it shouldn't be or too small, meaning too weak. You know, the connection shouldn't be too weak. They should be kind of critical, close to the level in which there's spontaneous dynamics. One interesting project to pick up is to take the simple networks project and create some spontaneous dynamics. So these are networks that are randomly connected inside, but by virtue of being randomly connected, they can have some specific types of spontaneous dynamics. Now, what do these spontaneous dynamics look like? In this slide, I'm using this rather old paper from 1998. It's older than most of you. And so the paper has a network with 200 neurons with sigmoidal transfer functions that are recurrently connected without self-connections. And I should tell you a couple of more of these details. So it has an input. I should say the network has a bias that is also taken from each unit has a bias that is taken from a random normal distribution with a certain standard deviation. And so basically it's a randomized network with a randomized bias vector. You press play on that network and it already has spontaneous dynamics. I told you that in the simple networks that we have in the project, they can have spontaneous dynamics. You might not have had spontaneous dynamics when you were running it yourself. But this is a very cool project to take up because it's basically started for you. And the only thing you need to do is to tune it up according to the parameters on this into this paper. But ultimately then, all of these 200 neurons or 500, these days we can run big networks, 200 neurons will have certain activities. So, and they are going to be sending to each other. If you average the activity of all of the neurons at every single time step, we're talking about a discrete time step recurrent neural network. If you average their activity, you see here in the left side of the plot, an oscillation. That's coming from free. I mean, the biases plus the randomized recurrent neural network inside produce spontaneous dynamics. If you now give the network a random input, So notice how many times I'm using the word random here. It's a random matrix, random bias, random input, everything random. And then the stimulus force dynamics are the dynamics of the network now with that random input clamped. So basically it's a constant input that has been added to the network. And you look at this time series and say like, well, that's funny, but I don't quite see what you're getting at. Let's look into the right side plot. This is called a first return map. And the way that the first return map is assembled is like this. For every time step, you take these 200 neurons and you average their activity. You don't care about anything specific. So at time 1, you average the activity of 200 neurons. You know it's a sigmoidal neuron, so it's going to be the average of 200 values between 0 and 1. And you plot against what's going to happen at the next time step. So on Y, you have the next state average. So for every given point here, this bottom graph is T. This bottom axis, T, and the vertical axis is T plus 1. So this is called a first return map. And it's a type of Poincaré map. We're not going to get into that today. But I will tell you, and what is quite funny, is that, say you have an initial condition and it stay here. Then you find yourself in this cloud, and your next output is going to be this guy here between 0.5 and 0.51. So then when you get that input, it's going to have an output. So for every input, you're basically plotting what is going to be the next state of the network. Questions? Because then I'm going to get to the conclusion. So this is on the x-axis, you have the average of 200 units at time t, and at y, you have the average of 200 units at time t plus 1. And now you're looking at the cloud and saying like, whoa, I don't understand the cloud. Any guesses what the cloud is? Let's discuss this cloud. If you understand the first return map, first questions about the first return map. Now let's try to discuss the cloud.
It represents the way in which T relates to T plus 1?
Yes, it does. And for a specific recurrent neural network, a specific random matrix. Now, one thing you should realize here is that once all of these parameters of the networks are random, wouldn't you expect that the state would be all over the place? I mean, that you would basically have like a map of points like everywhere.
Yeah, and here is some pattern.
Not only is some pattern, this is a lower dimensional manifold. It looks like it's much smaller than the 200 dimensions we have available. So it's basically occupying, in neurodynamics, I would say that it's occupying a smaller volume of the phase space. So it is actually concentrating itself in a manifold. And that manifold happens to be, I can tell you, chaotic. That means that very small differences in input will make orbits diverge. This goes a bit far, but in any case, it has sensitivity to initial conditions. But even if it has sensitivity to initial conditions, it is constrained onto a relatively small volume of phase space. So the kinds of things that this network can do are not infinite. It cannot produce any given pattern of output. It can produce a type of pattern output that looks like the thing that you're looking here on the left. I mean, there's only that you have to imagine 200 neurons here on the left. So these are 200 neurons, and they're going up and down. and they're producing this kind of like oscillation. But this oscillation has more structure than this one-dimensional representation in the time series lets you see. So these are the time steps. So, time steps. There's more interesting structure. And it's even more interesting that once you give an input to this network, which is random, you reduce the dynamics of the network even further. This little line you see here in the bottom is basically the one-dimensional manifold of the stimulus force dynamics. That means that once you gave the network a certain idea, you told him banana, the sets of possible decisions that the network can have, like the space of possibilities, reduces. So you have a reduction of variability that is related to the input data. This is so cool. We're saying that there is a latent, for any given random network, there is a latent something, a space of possibilities that it can become. And when you give an input, the space of possibilities is reduced. Now, the paper here makes the point that this is likelier that you will see a reduction of dimensionality than not. But it's not happening for every network. You have to randomize the network a couple of times to see these sort of like critical manifolds, and it has to do a little bit with the zone of criticality, not a little bit. It has to do a lot with the zone of criticality of this network. That's why people sometimes say that the brain has a critical state. Not only the brain has a critical state, this has been observed in the brain. So this is a paper in Nature Neuroscience called Stimulus Onset Quenches, Squeezes Neuronal Variability. And it's a widespread cortical phenomenon. Here they have a set of experiments where they have shown that by recording the brain in many different ways, in many different paradigms. Let's look here like on the right side of this figure first, okay? So, or I said right side of the figure, I mean left side. So let's see here, for example. These are possible types of a cross-trial firing rate variability. For one thing, you can have different responses, and when you give a particular input, the response variability quenches. Another way is when you give the stimulus, the neurons basically spread themselves along. Or another way is that they converge onto a single value from up and down, the mean rate. So there are different ways in which we can reduce variability just to have a mindset. Then let's go for the one on the top here. They use the Fano factor as a measure of variability. The Fano factor is the mean divided by the standard deviation of a process. So if you have a spiking rate and you want to find out what the variability is, you divide, what did I say? No, so it's the standard deviation by the mean. I actually sometimes I confuse. So should be, you're basically normalizing the variability by the mean. So it's basically standard deviation divided by the mean, clearly. So you have the standard deviation divided by the mean, and that's the Fano factor. You can do that for firing rates, clearly. In the top, there are two experiments actually. I've already singled out with my square two experiments. This is experiment number 1, in which you produce a random grating to a cat looking at the screen, and you see in V1 a reduction of variability. So the Fano factor here is being reduced. Is this too small? Can you see it? Stop me if you don't. Now in V4, an oriented bar will reduce the variability of the activity of the brain. This is like saying that once you present something to the brain, converges onto a set of activities that that has less variability. It is essentially like the slide that just shown you before. There is a reduction of dimensionality of the spontaneous dynamics of the brain. If you have sliding grids, they produce motion illusions. You have a reduction of variability in MT, which is the area of the brain that does motion recognition. Same thing if you have random dot patterns. Even if you're presenting random dots, if there's a little bit of coherence between the dots so that you see like overall motion in a particular direction, you have reduction of variability. In the lateral interparietal cortex, you have reduction of variability with covert attention tasks. In reaching areas, you have reduction of variability during a motion. So the examples abound. We have here more. Now this one is reduction of variability on the orbital frontal cortex at the administration of a reward. And this is more coherent random dot movement in MT. Now this is substantially discussed in this paper, all of these, and I definitely recommend it as a read. By the way, if a paper is old, it shouldn't matter, right? I mean, we all know that we're standing on the shoulders of giants, right? So it's a matter of how you assemble the puzzle together. This is what I had for our first block today. I wanted to give you the sense that randomly recurrent neural networks with spontaneous dynamics, they have something like a reservoir of possible things it can do, even if it's random. And when you produce input to it, you constrain it. You create sequences of like lower dimensional sequences, easier sequences to follow for the brain. And I didn't show you many slides, I mostly talked, but because the idea is truly very simple. You have a randomly recurrent neural network. For certain parameters of the randomization, you have criticality. And if you have criticality, you have highly complex, but structured, deterministic time series and outcomes. And from these time series now, you can, by producing input, you have the reduction in dimensionality. In the next block, I'm going to tell you about Hopfield networks and echo state networks. In echo state networks and liquid state machines, what we do is we use the power of a randomly recurrent neural network to train and produce complex motor sequences, or even sequences, syllables and things like that. And that's why it's called a dynamical reservoir network. So even though you have a random network, you can actually use that randomness to produce things that are specific. And we'll get to that in a second. So now it is 10 to 10. Oh, it's already 7 to 10. And I am opening to questions, and then we can resume at, say, 10:10.
I have one question.
Sure, please.
On the 5th slide, when you presented the functions, for instance, it was pattern recognition and the neocognitron.
Mm-hmm.
So you mentioned that the signal propagation might as well serve as the to fulfill the prediction, the function of prediction.
Yeah. So the recurrence, right? It definitely creates a prior. That's for sure.
And also assuming that we know that perception can be quite quantal. What I mean is that we know that there are certain self or certain characteristics, and everything. Perception is just holistic combination of all these. Can't we use this network to model, for instance, hallucinations? Because I would love, I personally think the hallucination also might be that rather than they might be the combination of this quanta that we see. So why can't we use recurrent neural networks in this function based to model deviation in this network?
It's always about the level of metaphor, and the question is how you want to convince your audience that you're showing something that is actually true to the system itself. But yes, people have been using so have you ever heard about PredNet?
No.
So PredNet, I'm going to just type it here on the. So PredNet is a network that is supposed to predict what the next image in a video will be. And after you train it via backpropagation, but it's a feed-forward neural network that, given an image, it should tell you what the next image is. So the error of the image is basically it produces an image. You give it an image, it produces an image, and the error is by how much they vary.
Yeah.
So if you now use the network that has been trained to predict images, and it can predict like future fairly well in, half a second, 1 second from here, it can predict how things are changing, because ultimately the sensory manifold is connected, and it's continuous, and so it uses that information to train the network. If you now present a visual illusion to it, it will detect motion and try to infer where that thing is going. Remember the illusions that Josh shown with the black, the high contrast illusions that you have like wobbly sensations.
Yeah.
The PredNet sees them. I mean, it's basically like saying that this network that has been trained to predict the future is also confused when something looks like it has motion in it.
Okay.
So this is one way. Now hallucinations are more complex, clearly, but I wouldn't be surprised if one was creating spontaneous dynamics in semantic spaces. One's essentially creating some dreams, and it's not unlike the gibberish that often is produced by some of these IGP3. What do we call it? GPT-3. These speech production bots.
Because also on biological level, the thalamocortical connection is recurrent, which is responsible, which is the hub for perception, right? Basically, so yeah, I think it seems not very.
Yeah, and it's recurrent, free recurrent loops.
Yeah.
So like basically has embedded recurrent. Thalamocortical connections is recurrent. Thalamo-basal ganglia connections are recurrent, and pontine cerebellar connections are recurrent.
Yeah. Very complex. Can I ask one more question?
Yeah.
It's from neuroeconomics, this decision making. I have a question about mutual inhibition in basal ganglia. Is this a model or basically a behavioral experiment or neuro?
There is both. I mean, there's a lot of data on mutual inhibition. I mean, so when I put something here, it's more than a model. There is a model. In Nango, if you just went and opened up Nango, they have a model that is called the basal ganglia. And what it's supposed to do is supposed to create sequences. In fact, it's one of the potential projects I put online. Just because I think it's a nice model to unpack to talk about in detail if someone decides to pick it up. So if you have multiple output systems, arm 1, arm 2, that system will tell you when to use this arm, when to use that arm, so how to sequence. And it works via the cascading inhibition from the direct pathways and the indirect pathways. Have you studied basal ganglia before?
To some extent, I cannot say that.
Yeah, I mean, the basal ganglia is beautiful, fun. So I think the data points to strong convergence between the models and the basal ganglia itself. There is the interaction between the subthalamic nucleus and the globus pallidus interior and exterior make you see what are the groups that have been suppressed in the context of taking a certain action. So you can see the electrophysiology. There's a paper. It's about the Libet hypothesis almost. It's a paper about how subthalamic nucleus is able to censor an action in the basal ganglia.
That Libet is the famous deterministic classical experiment.
Yeah, the free will.
The prediction of decision.
Yeah, this year we actually ended up not having our philosophy session, which is also fun, but we can also have it in other times. I mean, I had a lecturer coming in to talk about philosophy was Thomas Mollema, but then he got another kid, and then things got very complex for him, and so this year we're missing a full flight, but we can do this in the night of the BCI. There will be plenty of time to talk about free will. Ultimately, it's clear that we're looking into our own past, right? So whatever it is that we're perceiving right now has just happened. So we're living in the past, that's for sure. And if we want to be appropriate, we have to predict stuff to a certain extent. Now, how is it that the onset of action relates to what is actually the action or a prediction of the action? I think that this is a statement you can unpack in terms of how much energy you need for a network to finally produce to produce a functional behavior. So I think that the correlate is not, the correlate precedes does not indicate any consciousness, just indicates like the energy that has to be acquired until the point that something is, and consciousness is happily looking along basically as we do stuff. So it's that idea of consciousness is attention to memories. And so I think because consciousness is attention to memories, then free will is ill-defined in the present. It is well-defined in the past. But this takes us far. And I'm also, I think I'm rambling a bit because my brain is rambling. I think I'm